NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematical video, where we'll learn about factoring algebraic expressions using special formulas. Today, we'll explore how to factor an expression using the square of a sum of three terms identity. Let's recall the standard formula for the square of a sum of three terms. The square of a plus b plus c equals a squared plus b squared plus c squared plus 2, a b plus 2, a c plus 2bc. We can use this formula in reverse to factor expressions that match this pattern. Let's look at our example. A squared plus b squared plus c squared minus 2, a b plus 2, a c minus 2bc. To factor this expression, we need to recognize how it fits into our formula. Looking at our expression and comparing it with the square of a sum of three terms identity, we notice that there are some differences in signs. In the standard formula, all cross terms have positive signs, but in our expression, we have minus 2ab and minus 2bc. To make our expression match the pattern, we need to identify the correct values for x, y, and z. Let's try substituting x equals ay equals negative b and z equals c into the formula and see if we get our expression. When we substitute, we get a squared plus the square of negative b, which is b squared, plus c squared plus 2 times a times negative b, which is minus 2ab plus 2 times a times c, which is 2ac plus 2 times negative b times c, which is minus 2bc. Great! We see that with these substitutions, we get exactly the expression we started with. Now, we can apply the identity. Since we know that x squared plus y squared plus z squared plus 2x, y plus 2x, z plus 2yz equals x plus y plus z quantity squared, we can replace our substitutions and write a squared plus negative b squared plus c squared plus 2 a times negative b plus 2 a times c plus 2 negative b times c equals a plus negative b plus c quantity squared. Now, let's simplify this factored form. A plus negative b plus c can be written more compactly as a minus b plus c. So our final answer is a minus b plus c quantity squared. Let's summarize what we've learned. We used the square of a sum of three terms identity to factor our expression. The key step was to recognize that we needed to rewrite b squared as negative b squared and adjust the cross terms accordingly. Our final result is a minus b plus c quantity squared. For practice, try factoring x squared plus y squared plus z squared plus 2x, y minus 2x, z minus 2yz. The process is similar, and you'll get a nice factored form. In our next video, we'll explore another important identity, the difference of squares. Thank you for watching. Let's look at our example. We want to factor the polynomial a to the 6th plus 6a to the 5th plus 5a to the 4th minus 12a cubed plus 4 squared. The first step in our factoring process is to rearrange the terms to make patterns more visible. We'll group them in a way that will help us identify potential factoring strategies. In our second step, we'll reorganize the expression to reveal patterns that will help us factor. We'll write it as the sum of perfect squares and other terms. We see that the first three terms can be written as the square of a cubed plus 3a squared. The last three terms can be rewritten using common factors. In step 3, we recognize that this expression follows the pattern of a perfect square, trinomial. Specifically, we can write it as the square of the sum a cubed plus 3a squared minus 2a. Let's verify this by expanding the expression. Let's verify our factorization by expanding the expression and seeing if we get back our original polynomial. When we expand the square of a cubed plus 3a squared minus 2a, we should recover the original expression a to the 6th plus 6a to the 5th plus 5a to the 4th minus 12a cubed plus 4 squared. Let's summarize what we've learned. We started with the polynomial a to the 6th plus 6a to the 5th plus 5a to the 4th minus 12a cubed plus 4 squared. By rearranging the terms and recognizing the pattern of a perfect square, trinomial, we were able to factor it as the square of a cubed plus 3a squared minus 2a. This factorization technique can be applied to many polynomial expressions where perfect square patterns can be identified. The key to factoring complex polynomials is to look for patterns and algebraic identities that can simplify the expression. Practice recognizing these patterns will make factoring easier over time. Let's start by looking at the expression 4 plus 9x squared plus 16x to the 4th minus 12x minus 16x squared plus 24x cubed. Step 1. We'll first rewrite this expression in a more organized way, grouping the terms by the power of x. So we have 16x to the fourth plus 24x cubed plus 9x squared minus 16x squared minus 12x plus 4. Step 2. Now let's combine like terms. We have 9x squared minus 16x squared, which gives us negative 7x squared. So our expression becomes 16x to the fourth plus 24x cubed minus 7x squared minus 12x plus 4. Step 3. Now, our goal is to factor this expression. Let's try to recognize a pattern. One pattern to look for is a perfect square trinomial. Remember that for any expressions u, v, and w, we have the pattern u plus v plus w squared. That for any expressions u, v, and w, we have the pattern u plus v plus w squared equals u squared plus v squared plus w squared plus 2uv plus 2uw plus 2vw. Step 4. Let's try to find values for u, v, and w that would make our expression match this pattern. If we choose u equals 2, v equals negative 3x, and w equals negative 4x squared, then we get u squared equals 4, v squared equals 9x squared, and w squared equals 16x to the fourth. For the cross terms, we get 2uv equals 2 times negative 3x, which equals negative 12x. Then 2uw equals 2 times negative 4x squared, which equals negative 16x squared. And finally, 2vw equals 2 times negative 3x times negative 4x squared, which equals 24x cubed. Step 5. Now, let's verify that all the terms in our original expression match with the expansion of this perfect square. 5. Now, let's verify that all the terms in our original expression match with the expansion of this perfect square. If we expand u plus v plus w squared using our values, we get u squared, which is 4, plus v squared, which is 9x squared, plus w squared, which is 16x to the fourth, plus 2uv, which is negative 12x, plus 2uw, which is negative 16x squared, plus 2vw, which is 24x cubed. So combining the like terms, we get 16x to the fourth plus 24x cubed plus 9x squared minus 16x squared minus 12x plus 4, which matches our original expression. Step 6. Therefore, we can factor our original expression as open parenthesis 2 minus 3x minus 4x squared close parenthesis squared. This is our final answer. We've successfully factored the. Therefore, we can factor our original expression as open parenthesis 2 minus 3x minus 4x squared close parenthesis squared. This is our final answer. Let's look at our example. We need to factor this expression, 16a to the power of 12 plus 16a to the power of 8 plus a to the power of 4 minus 32a to the power of 10 plus 8a to the power of 8 minus 8a to the power of 6. Let's start by rearranging and grouping the terms in descending order of the exponents. This will help us see patterns more clearly. We have 16a to the 12th minus 32a to the 10th plus 16a to the 8th plus 8a to the 8th minus 8a to the 6th plus a to the 4th. Now let's combine like terms. We have 16a to the 8th plus 8a to the 8th, which gives us 24a to the 8th. So our expression becomes 16a to the 12th minus 32a to the 10th plus 24a to the 8th minus 8a to the 6th plus a to the 4th. Looking at this expression, we can try to factor it as a perfect square trinomial. Let's try to rewrite it in the form of a squared expression. Let's start by trying to group terms that might form perfect squares or other patterns. Following the steps from our input, let's see how this can be rewritten as a sum of squared terms. First, we can identify the term for a to the 6th squared, which gives us 16a to the 12th. Next, we see negative 4a to the 4th squared, which gives us 16a to the 8th. And we have a squared term, which gives us a to the 4th. Let's follow the solution approach shown in our example. We can rewrite our expression as a sum of squared terms and cross products. We have the square of 4a to the 6th plus the square of negative 4a to the 4th plus the square of a squared. Then we have 2 times 4a to the 6th times negative 4a to the 4th plus 2 times 4a to the 6th times a squared plus 2 times negative 4a to the 4th times a squared. Let's simplify these terms. The first term gives us 16a to the 12th. The second term gives us 16a to the 8th. The third term gives us a to the 4th. The fourth term gives us 2 times 4a to the 6th times negative 4a to the 4th, which equals negative 32a to the 10th. The fifth term gives us 2 times 4 a to the 6th times a squared, which equals 8a to the 8th. The 6th term gives us 2 times negative 4a to the 4th times a squared, which equals negative 8a to the 6th. Let's verify that these terms match our original expression. We have 16a to the 12th minus 32a to the 10th plus 16a to the 8th plus 8a to the 8th minus 8a to the 6th plus a to the 4th. Combining like terms, we get 16a to the 12th minus 32a to the 10th plus 24a to the 8th minus 8a to the 6th plus a to the 4th. This matches our simplified expression from step 2. Now, we can recognize this as a perfect square trinomial. Following the pattern in our example, we can write this as the square of the sum 4a to the 6th minus 4a to the 4th plus a squared. Let's look at our example. We need to simplify and factor the expression a squared plus 1 over a squared plus 2 times the quantity a plus 1 over a plus 3. Let's do this step by step. Step 1. We'll rewrite the constant term 3 as 1 plus 2. You might wonder why we're doing this. The reason is that we're trying to identify a pattern that will help us factor the expression. By splitting the constant term this way, we're setting up for a perfect square pattern that we'll recognize later. Step 2. Now we'll group the terms to start revealing the pattern. We can group a squared plus 1 over a squared plus 1 together. Keep the middle term with 2 times a plus 1 over a. Notice that the first group contains a squared plus 1 over a squared plus 1. This has a form that appears in the expansion of a perfect square trinomial. We're preparing to recognize this pattern in the next step. Step 3. Now comes the key insight. We recognize that this expression matches the pattern of a perfect square trinomial. Specifically, we can identify that this follows the pattern for the square of a sum with 3 terms, u plus v plus 1 squared. In our case, u is a and v is 1 over a. Let's substitute these values to verify. U squared is a squared, v squared is 1 over a squared, 2uv is 2 times a times 1 over a which equals 2, 2u is 2a, and 2v is 2 over a. When we collect all these terms, we get exactly our original expression. Now for the final step. Since we've confirmed that our expression matches the pattern of a perfect square trinomial, we can factor it directly. The factorized form is simply a plus 1 over a plus 1 quantity squared. Let's verify this one more time by expanding it. When we square a plus 1 over a plus 1, we get a squared plus 1 over a squared plus 1, plus 2 times a times 1 over a, plus 2 times a times 1, plus 2 times 1 over a times 1. This simplifies to a squared plus 1 over a squared plus 2, a plus 2 over a, which we can regroup as a squared plus 1 over a squared plus 2 times the quantity a plus 1 over a plus 3. And that's our original expression. Let's summarize what we've learned. In this example, we've seen how to factor a complex algebraic expression by recognizing a perfect square pattern. We started with the expression a squared plus 1 over a squared plus 2 times the quantity a plus 1 over a plus 3. We used several key strategies. First, we rewrote the constant term in a way that helps reveal the pattern. Second, we grouped terms strategically. Third, we recognized the pattern of a perfect square trinomial. Finally, we expressed our answer in the factorized form, a plus 1 over a plus 1 quantity squared. For practice, try applying this technique to similar expressions, like b squared plus 1 over b squared plus 6 times the quantity b plus 1 over b plus 9. Today, we'll work through an example step by step. Let's begin with the following expression. A to the power 8 plus 10, a to the power 4 plus 4, a to the power 6 plus 12 a squared plus 9. Step 1. Our first step is to reorder and group like terms. We'll follow the rule for the square of a sum of 3 terms, which states that u plus v plus w all squared equals u squared plus v squared plus w squared, plus 2 times u times v, plus 2 times u times w, plus 2 times v times w. Now, let's reorder our original expression to match this pattern. However, we need to adjust the coefficient of a to the power 4. We currently have 10a to the power 4, but we need to split this as 4a to the power 4 plus 6a to the power 4. This will help us match the pattern of a perfect square trinomial. Step 2. Now we need to identify what u, v, and w are in our expression. Based on the pattern we're trying to match, we can identify u equals a to the power 4, v equals 2a squared, and w equals 3. Let's verify this matches our pattern by computing each term. U squared is a to the power 8. V squared is 4a to the power 4. W squared is 9. Next, the cross terms. 2 times u times v equals 2 times a to the power 4 times 2a squared, which is 4a to the power 6. 2 times u times w equals 2 times a to the power 4 times 3, which is 6a to the power 4. 2 times v times w equals 2 times 2a squared times 3, which is 12a squared. Let's visualize how these terms match our original expression. We can color code each term to see how they correspond to our identity. Step 3. Now we can apply the perfect square trinomial identity. Since all the terms in our expression match the expanded form of the square of a sum, we can factor our expression as a to the power 4 plus 2 a squared plus 3, all squared. Let's verify. This is u plus v plus w, all squared, which matches our original expression. And there we have it. We've successfully factored our expression into a perfect square trinomial. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.